doing that now. And yeah, somebody mentioned here that the dates on the syllabus are a bit messed up. That's true. I'll say a bit more about that in a moment. But anyway, yeah, so welcome to Math 55. Okay. Or maybe I want to write black. Discrete math. And in this lecture, so let's see, first I'm going to give you a sort of broad intro and say a bit about logistics. And then I'm going to cover two topics from chapter 1. One is propositional logic. And the other is logical equivalence. That's the plan. So let me start by saying a bit about this course. So what is discrete math? Well, I mean, okay, there are a number of definitions, but the word discrete, really what it refers to is it's math where we study discrete mathematical objects. Which, okay, it sounds like I'm just kind of kicking the can here because I haven't said what discrete is. So discrete objects are objects that are not continuous. So it's actually best defined as what it's not. And examples are things like, the integers, like, okay, -1, 0, 1, 2, etc. Or like what's another example of a discrete object? Like a network, like a graph in computer science. And or a deck of cards, or maybe dice, the outcome of a roll of dice. These are all things where you can't change the values continuously. So this is different from things like real numbers, or vectors, which you study in math 1A or 1B or 54 or whatever, which are objects that can somehow change continuously, that you can you can slightly move them around and you still have the same kind of object. You can't do that with integers, right? And one sort of high level analogy is that you can think of these as being digital objects, that they're either this or that, but and you can't continuously change from one to the other, and you can think of these as being analog. So discrete math, okay, that's what discrete math is, but what is this this course? This course really has a bigger purpose than just study of these kinds of objects. And really what differentiates it from previous courses is that so far in courses like 1A or 1B, maybe Math 54 or Math 53, so basically calculus and linear algebra, the emphasis has been on using existing mathematics, on using existing mathematical theorems usually. For example, I don't know, the product rule for differentiation, right? Or maybe the quadratic formula, right? So minus, like, I guess you know what I mean by this. So these are, so it's a bit of a simplification, but in previous courses you mainly learn to apply some existing in some sense, algorithms, where the problems are, in some sense, what you need is a skillful application of these existing algorithms. And what's really new and exciting about this course is that we're really going to learn how to do and create new mathematics. So doing and creating new mathematics. Okay, so by that I mean, like, what is the process by which people come up with these theorems, and how do they know that they're true, right? So what are mathematical truths? And how do we establish them? So in that sense, the type of work that we'll be doing in this course is different in two ways. So the first difference is that there's a big emphasis on mathematical proofs. And proofs are something that you're not required to already know about. And so really we're going to spend a lot of time on what is a proof, how do you write a proof, on how do you read a proof, speaking mathematical proofs. So you can really actually think of this as a writing course in a sense. There's a lot of writing, like English sentences, whereas in previous courses, it's maybe a lot of formulas and calculations and things like that. And writing is really important. So, something, I mean, I studied also English literature when I was an undergrad. And what my advisor told me is that clear thinking and clear writing are kind of necessary for each other. It's hard to do one without the other. And we're going to emphasize this a lot in this course. That how can you use, good writing habits to clarify your mathematical thinking? And the payoff for all of this is quite broad. I believe it generally will make you better at solving problems in all aspects of life. Generally, it will help you think clearly. And of course, it's also the gateway to all higher mathematics courses, which are all oriented toward proofs rather than just calculations. So just out of curiosity, I just want to see like what, I just want to see what majors people are, if you know your major. So could you, I don't know, just type in your major in the chat. I just want to get a sense of where people are coming from. Okay, great. A lot of math and a lot of cognitive science. Yeah, I understand this is a required course for cognitive science, some psychology, music and math, physics and math. Okay, cool. Yeah. So good. Okay. I'm planning to do a lot of demos and examples in this class, and I'll try to make it relevant to your field. But anyway, even if you're not doing higher mathematics, this will help you. So that's sort of high level idea about what the course is about. I'll say a little bit about logistics. So I guess I should introduce myself. So my name is Nikhil Srivastav, and you can just call me Nikhil. I have been here for 6 years, and I actually work in discrete math. I work at the intersection of discrete math and linear algebra and computer science. And we have 6 GSIs, and which I guess you can look up what section you're in, and you'll meet your GSI soon next week. And let me briefly just say what the resources for the course are. So the resources are we have lecture on Tuesdays and Thursdays on Zoom. I have office hours twice a week. and the hours are posted on B courses. There are discussion sections on Mondays and Wednesdays, and this course has a lot of discussion. It has 4 hours of discussion a week, and I think it's really necessary and helpful, since this really is different from the previous other lower division math courses. There's a textbook, which is Rosen Discrete Mathematics, 8th edition, and you'll need this to do the homework. A lot of the homework will be assigned from the textbook. Let's see. There's Piazza, which is an online forum for asking and answering questions. So yeah, feel free to ask questions on that. I feel like the learning experience is really much better if you're interacting with other people rather than doing it by yourself. And me and the GSIs will of course answer questions on Piazza as well. And yeah, those are the course resources. I should say all the course materials will be posted on B courses. So you do need to have access to B courses, and you need to keep checking B courses. So homework, readings, announcements, videos of the lectures, etc., are on B courses. And the schedules on B courses too. And as somebody pointed out, it looks like, yeah, the dates are a bit messed up because I actually just copied the table from last year. I'll finalize the schedule right after the lecture today, but generally that's where you'll know what's going on. And I will post readings from this book, Rosen, in advance, and it's most helpful to read those before the lecture, or at least skim them before the lecture. So those are the resources. And then what's the work for the course? Well, so there's weekly homework assigned from the book, and one weekly untimed quiz covering the previous week's material. So untimed means it'll be like a 24-hour quiz online. Everything will be released online, and it's open book. And this will be due on Wednesday mornings. All this information is on B courses, by the way. There will be 2 midterm exams, 1 final exam. All exams in this course are untimed open book exams. Okay, so yeah, we're going to use the honor code. And yeah, so in particular, you don't have to worry about conflicts with your final exam time. Many people emailed me about this, but we'll have again 24-hour exam period, and you'll be able to find a slot in that to do the exam. And then finally, the grade is 40% the midterms, 40% the final exam, and 15% quizzes, and 5% homework. And we will replace the lower midterm score by the final if it helps. So again, all this stuff is written on B courses. But yeah, that's a rough summary of how the course will be run. So yeah, so before I get into the actual content, any questions about anything I said so far? So in general, yeah, if you want to ask a question, just unmute yourself and ask the question. You know, one of the nice things about online is everybody can sit in the front row. So.
Hi, I have a question in regards to discussion.
Oh, okay. I guess you got muted. Okay. Well, actually, I guess in the interest of time, could we maybe focus on any conceptual questions besides the logistics? So all the logistics questions we can we can handle in office hours or by email, or you can just ask your GSI. But are there any questions about what I said before, about the high level intro to the course?
Is this a course that we needed to take previous math courses to understand, or?
That's a great question. So no, you don't. Calculus is not a prerequisite. Linear algebra is not a prerequisite. There are actually almost no prerequisites. So that's one of the beautiful things about this, that we really start from scratch. So, I mean, it's good to have experience with math because, again, I mean, there is a lot of problem solving. So in that sense, that's helpful, but you don't need to know any particular math.
Thank you.
Is there a rule of attendance in sections and lectures
No.
for grade? Okay.
Is there any programming involved in the class?
Nope, there is no programming involved in the class. There are a number of exercises in the book, optional exercises that involve programming, and I will occasionally list those because I think many people in this class are also doing computer science. And this is, yeah, this course is absolutely essential for computer science. So if you want to do programming, you can, but it's not required.
For submitting our homework and assignments, will we need to learn like LaTeX? I know like some people from previous semesters, I've seen them like.
No, you just need to handwrite and scan everything. So
Okay, thank you.
We can use LaTeX though, right?
you can if you want. Yeah, sure. Yeah, I don't mind. But
where should we submit the homework on B courses?
so the homework will be submitted on Gradescope. I guess I should have added that as a resource. So again, the link, the instructions for joining Gradescope are on B courses under the syllabus page. Gradescope is, yeah, it's an online assignment and exam submission system that we'll be using throughout the semester, and which probably you're using in other courses as well. So yeah, just go to B courses under syllabus and all this information is there. Okay, so let's begin in that case. So I'm gonna start talking about propositional logic. This is section 1.1 of the book. And to motivate this, let's think about what is math actually? What is mathematics? So I mean, philosophers have discussed this for, I guess, centuries. And one definition that's relevant to this course, and which is true in a sense, is that mathematics is the science that draws necessary conclusions. And okay, so this is due to Peirce from the 1800s. And what does draws necessary conclusions mean? Well, really, it just means that the motivating question here is, if you know that something is true, then what else can you conclude is true or false, right? So this is what we mean by mathematical truth. Given some true statements, what other true statements can we deduce? And in this sense, true means like absolutely true. The notion of truth is, that's what the word necessary means, is in some sense the strongest notion of truth, which is absolute truth, which I'll define in a moment. And this is really different from many other fields of study. For example, in physics, truth is determined based on experiments. right? It's not it's not this notion of absolute truth, whatever that is. Or, you know, in I don't know, in literature or in poetry, truth means something else. It's something, I mean, in some sense, the truth of a poem is ultimately something that's it's an emotional truth. It depends on how it resonates with the reader. And, you know, in other fields like religion, and sometimes even politics, truth depends on, you know, some psychological process like faith or something like that. And in math, we have this notion of absolute truth that depends on mathematical proof. And so propositional logic is a framework for thinking about this idea of necessary conclusions that was invented by Aristotle, or at least recorded by Aristotle in, I guess, 2300 BC. And so let me begin by telling you what this is. So the key definition is the definition of a proposition. So a proposition is a statement which is either true or false. But not both. Okay, so we're going to use the letters T and F to abbreviate true and false. And you know, let's look at a few examples just to get a feel for what is a proposition and what's not. Well, okay, yeah. So so here are some statements, and we'll check if it's a proposition or not. So, okay, here's a statement, 2 + 2 = 4. So is this a proposition? Proposition is just something that has to have a truth value. So either true or false. Sorry, what just happened to that page? Oh, I just skipped a page. Okay, that's fine. Well, yeah, so this has a precise meaning. And so yes, it is a proposition. And what is the truth value? So truth value is just whether or not it's true or false. The truth value is this is true. Here's another statement. Wow. Okay. Is this a proposition? Not really, right? I mean, it's clearly something that we say a lot, and it communicates something, but it's not a statement that's either true or false. So this is not a proposition. It doesn't have a truth value. I guess here's another statement that's maybe a little more interesting. X + 5 = 7. Okay. So any thoughts on whether or not this is a proposition?
I would say no, because we don't know what the value of X.
Yeah, exactly. So this is a well-defined statement, but it doesn't have a clear true or false value. So no, it's not, because we don't know what X is. If we knew what X was, then it would, right? And then, okay, you can have statements like, I don't know, pigs can fly. Is that a proposition?
Yes, because
Yeah.
it could be true or false.
Yeah, it can be true or false. So yes, but this happens to be false. Okay, so the you know the key point is that in order for something to be a proposition, it has to declare something, and it has to be specified precisely. So to be true or false, a proposition must be specified precisely. And the important feature of a proposition is we're not very concerned with how we decided it was true or false. Okay, we're defining propositions to be those statements on which we can agree that it is either true or false. We're not really concerned with how you got to that truth or falsehood. It might be hard to know whether a proposition is true or false, but as long as it has a clear meaning and it is either true or false, which in principle can be known, then that's a valid proposition. Okay, so any questions so far?
So the example with x plus 5 equals 7, that would not be a proposition because it's not specified precisely.
Yeah, or I mean, it was specified precisely, but it's whether or not it's true or false depends on what x is, and
Okay.
that's not included in the description. So again, we cannot say it's either true or false, but not both, because, well, we don't know, right? We'll get to statements like that in the next lecture. They're of course very interesting, but they're not propositions. Okay, so those are the building blocks in propositional logic, propositions, and the key thing is that they have a truth value, and a truth value is either true or false. So it's like a switch; it's either true or false. Now, just as in arithmetic, we have numbers and we can combine them to create other numbers, right? So recall, so you can combine numbers using arithmetic operations to get more numbers. We can also combine propositions using logical operations, and this is how we're gonna generate more propositions from a given set of propositions. So let me now introduce logical operators. So we'll define logical to combine propositions to get new ones. So there are three principal logical operations. Or operators. So here's the definition. So the first one is negation. The negation of a proposition P. So here I'm introducing a new kind of device. I'm using a letter to refer to a proposition, right? And you can think of this as a variable. Just, we use letters to refer to numbers all the time in calculus, right? Well, I can use a letter to refer to a proposition, right? One of these statements is either true or false. And this is called a propositional variable. And okay, it's just fancy terminology for something very simple. But okay, the negation of P, a proposition P, is the proposition it is not the case that P, right? So given a statement, like one of the statements over here, like pigs can fly, you can now negate it to get a different statement. It is not the case that pigs can fly. And you can always do this, right? And okay, so this is denoted not P. So let me put this in blue. This is the notation. And this is red not P. And this is a new proposition. And the truth, it has a truth value, and its truth value is exactly the opposite of the truth value of P. So for example, if I negate the statement, pigs can fly, well, that's the statement, it is not the case that pigs can fly, which is the same thing as pigs can't fly. Okay, so in English, of course, we have many different ways of writing this. It is not the case that pigs can fly is the same as pigs can't fly. But logically, it's very simple. And we can express what this operation does, the not operation, using a table, which is a very sort of, explicit syntactic way to express what it does. So you can express this relation using a truth table. This is so what that is well, you make a little table with two columns. One is the proposition P, the other is the proposition not P. And the truth table shows us how the truth value of P is related to the truth value of not P. So if P is true, then not P is false. And if P is false, then not P is true. It's a very simple table. So truth table is another device we're going to use to understand these logical operators. So this is the first one and maybe the simplest one, negation. It just flips the truth value. Okay, that's kind of boring. Let me show you two more that are fairly simple, but we'll quickly get to something that's kind of useful with them. So here, there are two more. So the conjunction of two propositions, P and Q, is the proposition P and Q. Okay, so you can do that in English.
Second thing to the operations?
Excuse me?
Is this the second factor of the operations or operators?
Oh, you're saying that there are three, right?
Yeah, because I'm seeing, is this the second one that you're talking about?
Yeah, okay, so let me number them. So the first one is not.
All right.
The second one is and, the conjunction. And this is denoted P, use this upside down V for and. And this has truth value, or it is true when both P and Q are true, and otherwise it's false. And this is sometimes read as P and Q. Okay, I'm not going to write that, P and Q. Okay. And okay, we do this all the time, and this is kind of not, there's nothing subtle here. Again, just to get familiar with this concept, I can write the truth table. So now I have three columns. I have P, Q, and P and Q. So those are my three. Maybe this shouldn't be in blue, but I guess it's okay. Those are three propositions, right? The first two are my given propositions P and Q, and then P and Q is what I get when I apply this AND operation to them. That's a different proposition. And what I can do with this table is I can express the truth values of the constituent propositions P and Q. Sorry, I can express the truth value of P and Q in terms of the truth values of P and Q separately. So what I can do is I can write down all the possibilities. So P is either true or false, because that's what a proposition is, right? That's the only thing we ask of a proposition. It's either true or false. And then Q is either true or false, and you can have all these combinations. You can have both true, or TF, FT, and FF. And the truth table of the AND operation is very straightforward. It's just true exactly when both are true. So it's true here, and otherwise it's false. nothing subtle here. It's exactly what we are used to in English. Any questions about this? Okay. The third one, which is slightly more interesting, is or, which is called a disjunction. The fancy word for that is disjunction. So the disjunction of two propositions P and Q is the proposition P or Q, denoted. Okay, sorry, I keep adding. Wait, did I just clear the page? Oh man. Okay, I'm clearly. Okay, gotta be careful not to do that again. Hold on. Okay, my Zoom is acting a little funny. Okay, this is kind of weird. Okay, well, I'm just gonna. Yeah, this is kind of weird. My meeting controls are suddenly gone, but okay. Let's. Okay, I think there's something buggy going on with Zoom. I can't write any. Just a second. Okay, so
Professor, you might want to just restart at this point.
yeah. Okay. The problem is I can't even exit the call. Just a second. Does it still look okay to you, or does it look kind of weird?
The screen is gray.
The screen is
Yeah,
gray.
it's all
Okay.
grayed out.
Okay, that's a really bad sign. Hopefully I can save this before quitting. Okay.